Okay, next I want to talk about some numbers to try to support what I just said. So let's first look at what software engineering is, a definition for that. The IEEE states that software engineering is the application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software, that is, the application of engineering to software. So basically what we want to do is we want to use engineering principles to design a good software, that we can develop it, that it is operational, that we know how to maintain it later on, and it's a systematic, disciplined, and quantifiable approach. So we want to be systematic, step by step. There's disciplined, so you need to keep track on your diagrams, on your consistency and so forth. Quantifiable, testable, make sure it is correct. We need all that in software engineering. Let's look at the CHAOS report. This CHAOS report is actually from 2011 to 2015. It's the newest one, up to date. And here you see the different years here. And here you see projects, if they were successful, challenged, or failed. Successful means they were on budget, on time, and had everything included that was specified at the beginning that the customer wanted. Challenged means the program runs, the project is not done, not totally complete, it might not have been on budget or didn't have every feature included or might have been done too late, but it is done, it wasn't a failure. And then you have the failed section, is basically that the development failed and the project never made it to market. And you see here in 2015 the numbers, which I think are actually really interesting, because 19% of projects actually fail. This is 1/5 of projects basically that still fail. And over 50% of projects are challenged, meaning they're not on budget, not on time, don't have everything included that was specified at the beginning. This is basically something, at the beginning something went wrong. There was an error in planning because we didn't get everything done that was supposed to get done. And only about 30% of projects are really on time and successful. Another CHAOS report, now also considering how big the project is. So we're looking from large or grand to small projects. And here the numbers are also really interesting, because you see that here many projects fail, and especially the ones that are medium or larger, while only really few of them are really successful. If you look at that, a grand project only has a success rate of about 2%. And this is something, especially in grand and large projects, these are actually the projects where design mostly is most important. Because in these small projects back here, you can probably still go with little design, but up here where you're really having the big projects that are often safety critical, you probably will not be able to do it without design. And therefore, you need a good design to be able to be one of the successful projects. This is what the whole course will be about, how to do good software design, and therefore hopefully land in here somewhere instead of in the failed or challenged section. Okay, some examples of software design. Software failures. Here is one thing, it's the Tarac-24 radiotherapy. It is a while ago, and what happened here, they had a radiation machine and it was programmed, there was an error in it, so it delivered an overdose. So basically meaning that many patients got an overdose and even 3 people died because of that. This actually led to studies where safety critical software was considered a lot to make sure that things like that do not happen again. The thing is, often when you're implementing something in the university context. It doesn't matter so much if you're doing or making any mistakes in your code, right? You might get some points deducted, maybe not even points deducted. So depending on what you do, but an error here in the university setting is usually not such a big thing. Like I said, it might be deduction of points, but errors in some system in the real world might lead to people dying because of that. And that is why the whole thing is so important. That is why, yes, software is easily changeable, software is uniquely flexible, but also easily breakable. You can make mistakes, and a little mistake just with a number might be double value. It might be a cast from one variable to another type. This might lead to something breaking, and this might lead to people actually dying, getting hurt, or a lot of money being spent. Let's look at a second example. Here actually it's not that somebody died, but you have a cost because of this error of about 500 millions. So what happens? There was an error in the floating point division algorithm. The lookup table they used was incomplete, so you had a small inaccuracy, so inaccuracy, and this led to that chips needed to be recalled, and this led to a huge amount of money spent, and this is a lot of time that was spent developing the whole thing and then recalling it and redesigning it and making sure that error was corrected. This was also something where formal verification, model checking, and higher order logic came into being, or being more popular to make sure that this doesn't happen, that things like that don't happen anymore. I want to show this. This is actually a really famous example of a rocket start. That's the Ariane 501, and as it says, it was a software disaster. The rocket started, everything seemed to be okay until a couple seconds after start where it exploded. And of course there was a huge investment and investigation what happened there. And the thing is, this was a software error. What they basically did is they reused software from the old Ariane and adjusted it. But the hardware had changed, things had changed. So, and they didn't adjust for it. So their idea was basically, when something goes wrong, it's caused by a hardware failure. That was their assumption. And then it should be shut down, because then something went wrong. But the problem was that many things shut down. And it was basically traced back to being a floating point error. So what happened there? It was a pretty basic small error that led to the Ariane exploding, costing millions. And this, of course, is something that should not happen. It's, again, software was reused. It was thought, well, it works, we can reuse it, right? You probably know the saying, never change a running system. But if your hardware changes, you should, of course, change your software as well. So, one important thing to know about software failures is usually it's not just one thing that causes the whole thing to crash. It can be. Like I say, it can be a variable name you change and that breaks the whole system, but it's often little things that work together, and this is what is also hard, because you can't always see all the things that work together and how, and this is why it's so difficult to find these errors. Let's look at some success stories. So we have the OS360, which is an older version of the now current IBM mainframe OS, successful, used a whole lot. This is actually a system that was developed 1960. I think pretty impressive. It's American Airline Reservation System. There are versions of it out there still used today for different airlines. We have the NASA's Apollo Guidance System. Just thinking about it, that was get to the moon and back with 75K memory. I think that is pretty impressive. I leave Excel in here because it's considered as a success story. I think it's kind of funny because I don't like Excel, but it is widely used. Many companies use it. I guess if you say Excel, basically everyone knows it. If it is really a success story, yeah, but it probably is a success story. That doesn't mean that I like it. And the Mars Internet Worm, which was actually really impressive. I'm going to give you links to all these so you can look them up if you are interested. But these things are considered pretty good software successes. So there are a lot of failures out there, but there are also a lot of success stories out there. But it is just not so easy to create good software. And you should be aware of that, and that is why we're doing the whole design course here. Okay, summary. Yes, design is important. We needed to create good software. We need to make sure it is correct. We need to make sure that if we're looking at safety critical system, that a rocket does not implode, we're not delivering an overdose or something. Of course, not all systems are that critical. If you're having an application on the computer, it might just be that it freezes or that something doesn't work. This is annoying, but it's not safety critical. But a lot of systems are safety critical. A lot of systems, it costs time and money if they don't work correctly. So it is important to create good software. Design is also important to help understand what the system does and how it works and how it does the things it does. Because if you need to change something and you have a code base of a couple thousand lines of code, a couple 100,000 lines of code, you might not be able to find exactly where you need to look. If you have a design for it, it helps you narrow down where you can make changes, where you can improve. And if you're doing bad design or implementation decision, not doing any design at all, it might be really expensive, like the Intel example we saw, a couple millions. It might cost life, like the overdose, or, well, just lead to failure and maybe having some people being annoyed by it. But it is really important, and that is what the whole design class will be about, to design good software.